Right, thank you. So we use technology to solve some pretty complex problems. That's kind of what our jobs come down to at the end of the day is we're problem solvers. And obviously with computers being able to automate more and more, our value comes in solving really, really challenging problems. And one of the challenging problems our industry is facing is how to find a good bar nearby to go have a drink. This one is Manifesto. If you haven't been there yet, I highly recommend it. It's a speakeasy. You have to text to get in, and then you have to go in a back door and go down some stairs and get some really great drinks. So it's definitely an experience, and it is nearby. Now, I pose this problem because I used to use it as an interview question all the time. It was one of my favorite interview questions. Not because I really cared that much about whether someone would actually have the right answer, whether they could actually give me the correct way to solve this problem. More because I was looking for how people responded to feedback. That's something I really value, and when I deal with people on my team is when we give them feedback, how do they respond to it? How do they adapt their approach when it's not working? And so I picked it intentionally because a lot of people got it wrong. I interviewed a lot of people throughout my career. I've been out in the industry, out of college for about 15 years now, so over the course of that, I just interviewed a lot of people. And even though there is really no right answer, there's always wrong ways to answer questions, and most people would get that question wrong. When asked how do they implement some sort of algorithm to be able to search for things that are nearby, most people would really struggle. A few people would get it right, and we'll talk about that later. And they'd struggle because at this time, unless you've taken an artificial intelligence class or a computational geometry class, the most likely answer that you would have would be binary search. Just use binary search. That's the search that everyone learns in college. It's really, really intuitive to work with. We all know how it works. You start at the midpoint, you check whether something's less or greater than, you move left or right based on that, and then eventually you find what you need. In fact, this is such an intuitive search that chances are your grandpa or your dad could describe it to you, just not knowing what it is. If you just ask them how they find things in the phone book, which we don't really have these anymore, or if we do, it's the thing you immediately carry and drop into the recycling bin. Now, everyone can do this. They can actually, go find a name in a phone book, understanding that you start in the middle and then you go left or right, depending on what you find. But laymen, people who don't have a technology background, tend to pick very inefficient pivot points. They pick the wrong part of the phone book to start in because they don't understand the distribution of names and they don't apply that knowledge. But they can follow the algorithm. What's missing when you have an answer like binary search is that binary search is dependent heavily on the idea of a sort. You have to be able to sort the data, and you also have to have a less than, greater than, equal to comparison function. You can get away with just less than. But in order to determine which way to go. And those are actually the essential ingredients of using binary search. That's the hard problem to solve, is what's your sort. So let's talk about how we'd sort in this problem space. So we have some data, and what we have are latitude and longitude. We know where we are, and if we're lucky and we're solving this problem, we know where the things we want to find are in terms of their latitude and longitude. And to kind of generalize this, I'm just going to talk about in terms of x and y. We have x's and y's in this scenario. And so at this point in the interview process, when somebody proposes to me binary search, or sometimes it takes the flavor that they'd implement a binary search tree, I ask them how they would sort, and they take a small amount of time to think about it, and they come back with, well, I can sort by x and then by y. And that's actually pretty easy to break. That's a pretty poor answer. And I'm a visual person, so how I think about and how I would explain to them why that was actually something that didn't work is I use visual aids. And so from that standpoint, if you look at, well, if you sort by x and then by y, what ends up happening is points that are closer on the x-axis tend to appear closer, points that are on the same x-axis value tend to appear closer, even if they're not that close on the y-axis. So you end up with a situation of like things all the way across the world that are on the same parallel are going to appear nearby. So it's a pretty broken approach. Now, really, really bad candidates at this time double down on this approach. When you're telling them that like this isn't going to work, they have to do something different, they just keep throwing and throwing and throwing more stuff at the solution, hoping that eventually it'll start working. At another point in my career, I got to evaluate code written by all new engineers that we were hiring in the company. and we gave them this problem that required that they write a regular expression, but we gave them some time pressure just to see how they'd adapt to the problem if we gave them time pressure, and think if they even thought to use a regular expression. And some of the engineers in that kind of situation would write what I called a fornado, which is they just keep throwing for loops at the problem over and over and over again and hoping that the problem would get scared away. And this is what sometimes I'd see in the interview process with really, really bad candidates, right? They double down on this sorting algorithm they'd picked, and they just keep throwing different things at it and hoping that eventually this will all work, this will all come together work. And I think this process of let's start with an idea, we don't want to give it up, it's not working, we're just going to keep throwing stuff at it, is how we end up with really, really bad code and really, really bad systems as a result, when the same kind of approach is taken at the architectural or design level. So I'm going to backtrack a little bit, and I'm going to tell a weird story about a road trip my sister and I decided to take last summer. We decided to drive from Cincinnati to Kansas City. She lives in Cincinnati, I live in Kansas City. And the thought was that it'd be a really nice bonding experience. We weren't really getting along recently. We hadn't spent a lot of time together, and we thought, okay, we'll just take a long car trip together, and then we'll bond, and we'll be better off for it. And I'm sure you can think about how that tends to go. And sure enough, in Louisville, when we were stocking up in bourbon, the car broke down. And it was my sister's car. She doesn't take care of things. It's one of the reasons we don't get along. I'm highly organized. She's not. And this guy, people in Louisville are incredibly friendly. They all wanted to help us. And this guy comes out of the liquor store where we bought all the bourbon, which is piled in the back of the trunk now. And he just starts bouncing up and down on the front of the car. And I'm looking at him like, what are you doing? And he's like, well, sometimes with these older cars, if you jiggle them, they start working again. And I was just so shocked that someone would try that. What we actually needed was a jump, though. The batteries died, we needed a jump. It was no jiggling required. But I feel like sometimes that guy represents some of the decisions we're making in the system. We're not stopping to think, and we're just bouncing on the front of a car. So at this point in the interview process, most people that actually do respond well to feedback, that are able to adapt, because they don't have a background in the algorithms and data structures they need to make the right solution, they tend to fall back to brute force. And brute force, basically, in this problem space of finding a nearby bar, given knowing where you are, is basically to iterate over all the data, calculate the distance, and then sort by distance and pick the one at the top. And you know what? I was actually okay with that answer. If someone gave me that answer and we had a good conversation getting there and they weren't resistant to feedback and they could reason about how it would work, then I would hire that person, because a brute force answer is better than the wrong answer jiggled into a mostly working one. That doesn't help anyone. So at this point, you might be really, really getting curious about what the right answer is, or you might be thinking, I'm a really mean interviewer and you never want me to interview you. There is a right answer. Some people did get it right. A lot of people got it right. The people who got it right all had something consistent about them, and that they were physics majors. I don't care whether someone has a computer science degree or not. I care that someone can reason about problems and knows a programming language in order to implement those solutions. So I ended up hiring and interviewing a lot of physics majors, and they would do great at this problem. And in particular, people who had a background in particle physics or large space collisions tended to immediately know how to solve this problem, because they were able to convert the problem I described to a problem they had already solved and knew how to solve. And how they solved it was, whether you're dealing with particles or you're dealing with space, you need to divide and conquer. So you take your big area that you're worried about, whether it's the state of Missouri, Kansas City, the whole world, and you treat it as one big rectangle. And then you cut it up into 4 rectangles. And then you cut those rectangles up. And you just keep doing that over and over and over again. And you end up with all these quadrants. We think of them as quadrants because every time we cut it, we create 4 spaces. And the rules about those quadrants are, we don't actually care if they're equal in space or not. We're not that worried about their actual, square mileage. In fact, sometimes it's better if you make them equal in terms of the things that are in them, the capacity they have to store objects. And once you have that, you need a way to define each quadrant. So one way to do it is you can actually take the center point and you say the center of this rectangle or this square is going to represent the whole thing. Or another way to do it is you create a bounding box and you say the corners are going to represent this thing. And once you have that way to represent each individual quadrant, you build a tree out of it. And every node in the tree has 4 children. Each child represents a quadrant of the parent. And when you get down to the leaf nodes, you end up with either, you can go all the way down to each leaf node only contains 1 item, or you can say at a certain point within that leaf node, you just have a list and you just go linearly down the list. It's up to you what you want to do. But the whole goal is to get to a leaf. And that's what you do to solve the problem, is you take where you are, you test which box you are closest to if you're using center point, or which box you're in if you're using bounding box, and you follow it all the way down until you get to the leaf. And the things that are in that leaf are the things you care about. So those are the bars you're going to want to go to. This was invented in 1974 by a couple of computer scientists, John L. Bentley being the most famous, the one you've probably heard of. He calls it a quad tree. And it's a really, really good answer. Now, John Bentley may be familiar to you if you've ever read Programming Pearls. It's a great, tiny little book. I got it as a gift when I was going to school for computer science. And it has a whole bunch of these little snippets of interesting ways to solve problems, interesting tiny little algorithms, things that have gone wrong in programming. But one of the things it's most famous for is it is the binary search, getting back to binary search, that everyone copied when they wrote binary search. So John had the first publication of a way to implement binary search, and everybody started copying it. Well, in it, he didn't really think much about integer overflow. And so it actually is buggy if you get to anything that's the size of a max int. So if you're searching like a very large file, then you're going to end up having a bug because of the way it was implemented. And so how this got to be famous is that Josh Block, and so if you're a Java programmer, you should know who Josh Block is, he copied this implementation in Java in the collections API, and then there was a bug. Oddly enough, John Bentley also was Josh Block's professor at one point. So some history there. So quad tree is a very good answer, not just because it solves the problem, is effective, and it's easy to reason about, but also because it can be generalized to more dimensions. So you don't just have to use it for 2-dimensional things. You can have octrees, which are 3-dimensional things, and you can keep going up powers of 2, and we all love powers of 2. The other thing that's kind of cool about it, and if you watched a previous Midwest.io talk that I did it on this topic, is it's actually useful for compression. It's kind of cool. You can take an image, and you can cut it up just like we were doing the space. And when you get to a block of that image that is all one color, you get to store just that color in the leaf node. And you can kind of minimize the storage space required for your image. So that's pretty cool. So this is my llama done as a quad tree. So that isn't the only answer, though. That's one of my favorite answers, and it fits with the theme of this talk, which it came from the 70s. There are also other answers. And getting back to binary search wasn't actually that bad of an answer. It would have been okay. The problem was actually where everyone went wrong is in the sort. They didn't really understand how to reason about 2 dimensions when you're sorting. Sorting is inherently one-dimensional. We don't think of it that way because we're always dealing with a lot of variables when we're writing all those silly Java comparators or whatever the language, like C++, you have your less operator. We don't think of it as linear or one-dimensional, but it is because it's ultimately a line. It's an order. And so this problem that I'm talking about, this problem of finding nearby things, well, you have 2 values and you need 1, and that's the challenge. So what happens when you're doing that less function or that comparator is that you're basically trying to make a single number out of the 2 numbers you have. And if you think about it, what you're actually doing is you're making a bigger number by concatenating the 2 numbers. The thing in your sort function that you check first gets the higher order bits, and the thing you check second gets the lower order bits. And that's bit concatenation. So a really, really, really quick hack around this to get you to a better sort is bit interleaving. You take the first bit of the first number, you take the first bit of the second number, and you just weave together those bits until you get your bigger number, but in a way that kind of, they have equal priority. So what I just described, that bit interleaving, has a name. It's called z-order, or sometimes it's called the Morton curve, is another way of talking about it. It was written by Morton in 1966. And it's really, really cool because as you watch it work, if you take these numbers, so here's my grid of every number, of each number in each dimension that I could work with. As you watch it work, it's interesting how it kind of moves through the system in order of this newly created number. So you would start here, and the biggest number in this grid is over here once you're done doing the interweaving, so you get 15 at the top corner. And then you can just walk through in a different order than you were expecting because of this bit interleaving, so it's kind of fun to watch. What it actually does is it makes these little Z shapes, which are kind of fun. And so I've inverted it for this picture, but there's your start and there's your end. And then if you want to go to even more bigger numbers, then you can kind of connect your Z's as these. So you can make your Z's into these little Z-shaped things. And then you can take that and you connect them as little Z's. And then you can take that and you can make one big Z. And so you're probably noticing this recursive behavior where I'm taking the smaller form of the problem and I'm stitching it together using the same principles to make the bigger form of the problem. And it is, but that also describes something else we see in math, and that's a fractal. So this Z-order curve, the Morton order curve, is actually a fractal. It's a space-filling curve, and there's tons of these, and they're really, really fun to investigate, and they make really, really interesting pictures and animations if you ever want to go look at them. The best one for solving this problem space is typically the Hilbert curve, which I'm not going to talk about because it's too old. It doesn't fit the time range I've defined. So bit interleaving can be extended to multiple dimensions as well, just like the octree. I mean, you can interleave as many as you want. Interestingly, last night at the social, I was talking to David Greenberg, and he was telling me that a friend of his is actually doing some research in how to vary how many of each bit you pick when you interleave in order to kind of get, when you have lower dimensionality dimensions, so variables in that sense, that you can actually not have them overpower the result of your sort, which I thought was pretty cool. So thanks, David, for sharing that. So we found our nearby bar. We found manifested. We've gotten through that problem space using some help from the 60s and 70s. Now we have a new problem, which is we got to get there. Now it's really easy to get there. You can just take the streetcar one stop and you'll be there. But we're going to ignore that for now. I've done public transportation routing. It's typically not this easy. And so we're going to pretend it's not. And we're going to switch from space to graphs. And to do that, I'm going to tell another, my sister and I get in an adventure story. So we were in Cincinnati again. That's where my dad lives. And we kind of got lost in suburbia. My dad lived in suburbia, and suburbia doesn't follow the normal rules that we all like to live by of things being at right angles and being named in a way that you can infer things about them. My dad's subdivision in particular is this weird tree structure, and everything has tree names. And it has tree names in a way that you can't possibly reason about it. Like if my dad's giving me directions, and he's like, you need to turn on Blue Spruce Drive, and then you go on Arborwood Court, and then you go on Elmwood Court, and then you go on Blue Fleur Lane, and then by the time you leave, you're like, wait, was it Blue Elm? Was it Elmwood Court? Was it Elm Street? I don't even know. Where am I going to end up? And this is before my sister and I had smartphones, which really, really dates us. But so we couldn't just go look it up and get directions on it. And we get lost, and we couldn't remember what roads to go on. And my sister's panicking, and she wants to kind of trace back our steps and drive to the nearest grocery store to get on a payphone, which also dates us the fact that payphones existed at this time. And instead I say, no, we're not actually going to leave the subdivision. What we're going to do is we're going to go right. At every single intersection, we're going to make a decision to go right. And she looked at me like I was crazy. She's not a computer science background. She's in more finance. But she thought I was really, really crazy. She's like, you're going to get us lost. We're going to go in circles. I was like, no, I know this subdivision is a tree. I know there's no cycles in it. We can always go right. And so we did. I just always made a right turn. And I think we only had to make 4 or 5 right turns. And finally, we got out. We got to my dad's house, and it was there. Luckily, we recognized it. Not all the houses looked the same. And so that approach is actually depth-first search. It's from the 19th century, so I'm not really going to celebrate it that much other than it was a funny story. My sister now will believe me when I tell her I know where we're going. I'm going to talk first about breadth-first search, which is another way to approach that problem. If we're trying to find something nearby, we don't really want to do depth-first search, especially if there are cycles in the graph or if things go on for really long distances because we'll just be driving forever. So it's more likely if you're actually going to try to plan a route and you have a paper map, you're probably going to use breadth-first search where you're going to kind of look around in circles at intersections and try to figure out your path. And those of you, this might be all review, and I don't care because I like pictures and I like to make pictures and have people watch them. So that's breadth-first search. That was invented in the 50s, so again, it doesn't really fit my pattern here, so we're going to have to pick something else. It also doesn't work very well if it's a weighted graph. If you have some measurement, like if we're trying to value time, and so we need to understand speed limits and distances, well then breadth first search doesn't really work that well. And so if you have some means where you want to minimize some cost, whether distance or speed or gas or Tesla charging station access, I don't know, you'll want to have an algorithm that actually allows you to leverage cost. And so the easiest one starts by having an open list, and the open list is the list of intersections you would like to consider but haven't considered yet. And you order that open list by sorting by the sum of all costs to get there, and whatever your cost function happens to be. And then you'll want a closed list, and that closed list will be all the things you've already visited. And you keep that because you want to kind of make sure that you're not getting in these loops, visiting the same place over and over again. And so working through that little example graph I have, you'd start out and you'd have A on your open list, because that's the first thing you know about. And you would look at all of its edges and all of its neighbors. And then you would add A to the closed list. And then you would add all of the things that you now are aware of to the open list, sorted by lowest cost. And then you'd pick the next lowest cost one, in this case is B, and you would look at all of its neighbors, and you would update your open list and closed list, and you'd move through that until eventually you find the thing you wanted, which is in this case, that item E. Now you should all be familiar with this one. This one should be no surprise to anyone in the room. I just didn't name it initially. That's Dijkstra's algorithm. Dijkstra's algorithm is the one algorithm that people know. Like when you talk to someone right out of college, that's like the one algorithm that everybody knows by name. They know Dijkstra's algorithm. And it's funny because it's so familiar to people that sometimes in that previous example I talked about in interview questions, I'd ask people how they'd solve it, and they'd say Dijkstra's algorithm. I'm like, no, this is not a graph problem. I don't know why you said that. But we're also not going to celebrate this one too much, even though we all love Djikstra, because it's 1956. What we are going to talk about is A*. I love A*. I learned it in college. I've used it for work. It's one of my favorite systems to reason about, or algorithms to reason about. It was in 1968. It's almost identical to Dijkstra's, except you have additional information, which is you have some idea about the suitability of a node that's external to the costing function you already have. And that idea about the suitability of the node is a heuristic. Most commonly, when you're dealing with routing in like a real-world scenario, what you'd end up using in this case is actually the line of sight distance. So things that are farther away in line of sight tend to be less suitable as a path for you. That gets a little hairy when you're in big downtowns and you got the wide loops that go around it. But generally speaking, that tends to be a safe heuristic. And so you use the same structure that you use for Dijkstra's. You have your open list, you have your closed list. But now the cost function's a little bit different because in addition to, or the sort function's a little bit different. In addition to the cost to get there, you want to add your heuristic value, and you're going to sort by that. And you're going to do the same exact practice of moving things from the open list to the closed list. And eventually you find your item, although a little bit earlier. Not a lot earlier. It's actually not this magic algorithm. You just find things a little bit early. We didn't have to close one additional node. So again, I'm a very visual person, so how I like to reason about this is that if you're dealing with breadth first search, you make one big circle. If you're dealing Dijkstra's because you're being smart and using that costing function to make better decisions, you get to cut off some of that circle and get kind of this fuzzy little cloud. I worked with an individual that worked on the routing algorithm prototype for Tesla, and he liked to call these fried eggs. It used to crack me up. And then he would write code that said, you put fried eggs in frying pans. And I was like, now you stop it. You're just making things confusing for other people. And then A*, which is the algorithm I love, looks more like an egg, like a lumpy little egg. Not a fried egg, but an actual hard-boiled egg. And it basically reduces the area that you're visiting when you're working through this algorithm. And this is really just the power of heuristics. Anytime you can have additional information in your search and apply it, you're just going to reduce the space a little bit about how you approach it. And of course, you have to have a good heuristic. You have to have one that doesn't go greater than the actual cost of something, and that's called being admissible. So when we look at this, besides visualizations, I also like to think about it in terms of math, because I got into computers because I was into math, not really because I was into computers. And so the way I think of it is like as functions. Breadth first search, you have this f of x equals a constant because everything's equal. Dijkstra's algorithm, you have f of x equals some costing function plus a constant. And then A*, you now have two functions plus a constant. And so when you look at it this way, it's kind of funny that we discovered breadth first search, then Dijkstra's, then A star in our field, because really the first two were specializations of the generalized form, which was the last one. So the last one actually captures the other two. The constant could be 0, the heuristic function could be 0, and now you have the other two forms. So that does not mean A star is always obvious or always awesome. There are certain rules that I think that you should apply in determining which one to use for your search problem. If all of your edge weights are equal, then who cares about your costing function or even your heuristic? Just look at everything in a circle. If you have some insights about your target, like if you actually know you have a costing function and you know something about where you're trying to get to, then you're probably going to want to use A star. But if you don't know anything at all about your target, then you're going to end up using Dijkstra's, and it's a really great algorithm. Now, another thing you have to consider is what's your most expensive operation. So when we talk about visiting a node, we talk about closing a node. Those are the terms we tend to use. It tends to require some I/O. So usually you're reading some information about that node from a disk. And so a lot of times when you're doing that, that's your most expensive operation. I/O tends to dominate a lot of our concerns in this field. And so in that case, you want to use some heuristic to reduce the number of disk reads or I/O you have to do, and that's why you want to use something like A star. That being said, though, if you live in a world where your entire graph can fit in memory and there is no I/O, or you find that you're actually CPU bound, like the cost to calculate your heuristic is really, really expensive, and so you need to save actual CPU cycles. Well, in that case, you're going to want to use Dijkstra's because you're going to minimize your calculations, and you don't really care about reading the information about the nodes. So how you pick it just depends on the environment that you're in. And this kind of speaks to a little bit of machine empathy and understanding the system that you're working with. But let's talk about memory a little bit. One of the biggest challenges I found working with whether Dijkstra's or A star is actually managing the cost of storing that closed list in memory. You know, A star, you have this little, goofy looking egg that you're working with, and all of that egg has to be stored in the closed list in order to reason about whether you've visited something before or not. That's the whole point of the closed list, is making sure you don't revisit. And it can get kind of expensive. And sometimes kind of expensive in a way that's not really providing a lot of value, because if you have a really good heuristic, you're going to pull towards the destination, and you're not going to spend a lot of time looking back at the source. And so one of the approaches that I've done to actually deal with this kind of expensive storage of the closed list is actually to prune it, is to get rid of it, because I'll take the risk that I might accidentally go back towards the start of my route at some point and have to revisit a node in order to save the cost of storing that whole darn list of things I've visited in memory. And then you just keep moving that pruning process down based on some threshold until you've saved the memory you need. So when I was working on this specific problem around, my closed list got too big and I didn't know what to do with it, a lot of people on my team were playing with Bloom filters, and they got really, really excited about Bloom filters as a possible solution. And so everybody loves to run into your office and tell you they have the answer to your problem. So Bloom filters are really cool. If you haven't worked with them or read about them, this will be your very quick, graceful introduction, and then go do some exploring. They're 1970, so another 70s algorithm. Burton Howard Bloom. Not pictures of him. For some reason, he's not a famous enough computer scientist to have a lot of photos out there. I really wish we had more celebrity computer scientists, like that people just knew their faces, and then we could have fun memes with it. Like, whenever somebody tries to add too many people late in a project to make it go faster, you could just send them a meme of Frederick Brooks, and people would just be like, not again. Mythical Man Month, read it. So the way a Bloom filter works is you pick a number of bits that you want to represent your set. And in this case, I have 10 bits, and that's because it's my presentation. I can have 10 bits if I want to. I don't have to adhere to powers of 2 in my presentation. And then you have, on top of that, you have k hashing functions. And k should always be much, much less than m. So your number of bit positions should be greater than the number of hashing functions you've determined. And then you take your data and you hash it by these series of functions you have. And then whatever number results, you set that bit in your Bloom filter. And what's really cool is that it's really, really easy then to understand whether you've seen something before, because you repeat this process, and if all of those bits are set, then you've seen it before. You don't have to visit it again in this case. So the challenge is when somebody proposed this idea to me on it being the end-all solution to my problem of having a closed list that was extremely large and consuming all memory, is that since we're hashing, we have collisions. And collisions mean false positives. And so what could end up happening is if I actually had used a Bloom filter for my closed list, is that the right route to get someplace could have had a collision with something I'd already seen. And then I would say, oh, I've already evaluated this. I shouldn't look at it again, and I would never, ever find the right route. So Bloom filters are awesome. They're really clever. They're really cool. But you have to reserve them for spaces where false positives are OK. They're not going to destroy your result. And so typically how these get used, and typically when people use Bloom filters, is in the space of some sort of mechanism to avoid a disk read. So basically, with a Bloom filter, you know for sure something's not there. You don't know for sure that it is. And so what you can do is you can actually set up a Bloom filter on top of your I/O operation and say, okay, if I see it in the Bloom filter, I know I need to go read it because I know it's in this disk, or I know it's in this hard memory. But if it's not there, then I know not to read it here because it's clearly not there. And so what you'll see is that actually Bloom filters come up in a lot of big data technologies, and in particular, the one I work with, HBase. And with that, let's get back to graphs. I'm going to talk a little bit about where I work. I work for Cerner, as Denise mentioned. I work in their population health organization. The population health organization is basically, in the simplest way, bringing together the world's healthcare information into one place and trying to make sense of it. It's different from how you traditionally think of Cerner, if you know of Cerner. Most people think of Cerner as doing the electronic medical record systems that support physician and nurse workflows. We work on the other side. We take that data, but we also will take any data we can get. We'll take payer data from insurance companies, from Medicare, Medicaid. We'll take data from pharmacies. We'll take data from patients. That's where Denise works. And basically, we take all this data together, and then we try to get it into a single standard data structure that people can reason about. We try to convert all these weird ways that nurses and physicians and hospital systems represent very common things like diabetes, and we try to use a standard terminology in order to convert it all so we all know it's diabetes. And then we'd use all these concept ontologies to roll it up into greater concepts. And at the end of the day, what we're really trying to do is identify people who are at risk for expensive, life-altering conditions before the medical system has to intervene in some sort of drastic way through surgery or other means. And in the system that we're building, right now we have 55 million unique people. I say unique people because one of the hard problems we have to solve is figuring out that two people are actually the same person, because they'll go into one hospital and they'll misspell their name. They'll go into the other one and they'll give them the wrong address. Right now we're at about 3 petabytes of healthcare data that we're dealing with. We have an 800-node Hadoop cluster that we do all this work on, and more data is always arriving. Hospital systems do not shut down and give us time to catch up with the data. I mention that because I gave a talk once at a university about our system, and someone came up to me afterwards and they said, why don't you just wait for all the data to arrive? So getting back to algorithms from the 60s and 70s and how they help us reason about these kinds of complex problems, we actually use a Reedy algorithm to do some of the work that we do. And we do that because the healthcare system is full of lots and lots of rules. We had this whole idea of evidence-based medicine, which is like, people do a ton of research and they come up with very clear guidelines about how people should be treated. But then it's really hard to disseminate those guidelines and that new research and evidence to doctors all the time. And so one of the things we're looking at doing is, can we incorporate some of that information, some of those new guidelines, and can we just let doctors know that they need to intervene differently and not require that they understand all the rules behind it? And so to do that, we kind of needed a rule engine. We needed to be able to take these series of premises about a patient, like if you are, you had this blood glucose result, or if you're this old, or if you're on this medication, that we know that something else needs to happen in your care, and that's the conclusion we can draw. And typically, we don't just want to draw a conclusion, we actually want to have someone take action. We want some sort of care provider to intervene on your behalf. So rules are typically represented in systems as tuples. So you have a series of premises represented, and then you draw a little pretty arrow, and then that's the action. And that can be more than one action that you want to take. And a lot of times when you're dealing with rule systems, we like to say LHS because we like to confuse people, and then RHS for the other side. The cool thing about rules is that there's interdependencies between them. Like the result of one rule could be input to the next rule. And so what you end up with is these knowledge graphs, these directed acyclic graphs of knowledge that you have to reason about. And you want the dependencies to be impacted by prior knowledge when you're working through it. And that's what the Reedy algorithm does. It basically structures all of this information you have by having different types of nodes, starting with the root node, and then having these type nodes, and then these selection nodes, and then these negation nodes, and join nodes. And those operations are actually as simple as they sound. The root is where you start. The type node lets you know what types of knowledge you're interested in, basically what data types. The selection nodes allow you to prefer certain information, select from it. Negation nodes allow you to say not this. And then join nodes allows you to combine the results of previous knowledge into something new. And then you have terminal nodes, which is where you want to end up, which is what action you want to have. Now, the Reedy algorithm actually introduced this idea of like alpha and beta memory to allow you to store sort of intermediate states and decisions that are made in the tree, and that allowed for some greater efficiency. I'm not going to go too much into that because I could probably spend an entire presentation on that, but it was something that helped a lot with the performance of these knowledge systems. And so what we do is we might take some of the rules in healthcare that we have to deal with and convert them from this left-hand side, right-hand side, and make that graph out of them. And then we can actually reason about the system efficiently. I do have to cite that I stole this presentation from Ryan Brush from his, stole this slide from Ryan Brush's presentation, Retaking Rules for Developers. I didn't ask permission because I'm married to him. So all of these ideas and why I'm sharing them is to kind of share that sometimes our job is to find ways not to write code. A lot of times problems are already solved for us, like maybe we shouldn't be building an expert system from scratch, painfully one if statement at a time in Java. That doesn't make any sense. And I know nobody ever intends to do that. Nobody ever intends to build this massively complex, horrible to maintain system full of business rules coded into if statements and switch statements. And those things tend to evolve over time. And the reason they evolve over time is at some point nobody ever asked the question, is this gotten to the point that I shouldn't be building this anymore? That I shouldn't be doing it this way? I need to think of a more creative way to solve it. And in the case of rule engines, there's some established options. Jess, Drools, Clara. Clara is basically Reedy plus Clojure. And just to plug him, since I stole his slide, that's an open source project that Ryan has developed. So, back to another car story. This whole talk started out as a carpooling conversation with Ryan. We were driving around and we were talking about bad code we'd seen, bad decisions we'd seen. And the question that Ryan asked me is, he said, do you feel code reviews are supposed to solve this? And I said, no, of course not. Code reviews require a human to understand the problem that you're solving, to reason about it, and to pay attention to all the details. So the fact that we have code reviews should not suddenly solve the problem of we have this complexity and we need to make it cleaner. And I told him this story about how I was in a code review once and somebody was trying to balance like efficacy versus cost versus convenience in this healthcare problem. And they did it how we would have expected them to do it if they weren't aware of other options, which is they made something that was like a really, really elaborate sorting function, and they sorted things, and they picked the thing off the top, just like the interviewees did with the spatial problem. And how that thing got really, really hard to reason about. When it didn't give you the right answer, it was really, really hard to explain to the client why, well, we're doing this linear sort, and it doesn't always work out, and you just have to be okay with it. And so people would try to put stuff on top of it, like, oh, well, we'll just make a whole bunch of sort functions, and then we'll kind of balance them all, and then we'll do this like weird, elaborate, multiple linear sort, and then we'll like take the top 10 and then resort it, and take the next 10 and resort it. And that was, again, that bouncing of the car up and down and trying to jiggle the system into place as opposed to thinking about like what's really wrong. And so at the time, I didn't know about quad trees. I learned about them later in my career. But I did know that code looked really, really bad. It was a really, really dumb idea. But without being able to walk in and propose another solution, it was kind of hard to argue with the engineer that wrote it that, like, hey, there's a better way to solve this. I just knew intuitively there was a better way to solve it, but I couldn't explain it. Now I could walk in, I could say, maybe you should try a quad tree or an oct tree. Or I could be like, hey, maybe you should try Z order, and you should order these things differently. And I can also say, you sure as hell shouldn't write a tornado. And so this whole presentation is kind of a call to, like, sometimes the best thing to use is really old. It's already out there. Someone's already solved the problem. And we just need to refresh our memory and understand that if things look really, really complex, we're probably using the wrong algorithm. Even though we're happy to be out of college, sometimes it's a good idea to go crack open that old algorithms book. The Introduction to Algorithms Bible that we all had to work through is still very much relevant to the problems we solve today. And if you don't want to pull out that old book or you sold it back to the bookstore, you can always do kind of a depth-first search of Wikipedia where you just kind of explore all the computer science literature. Because your solution is probably out there. And to be honest, there's not a lot of new things anymore. It's probably from the 60s or 70s. So with that, I'm from '79, so I'm also a product of the 70s. I'm Michelle Brush. As I said, I'm an engineering director for Cerner. I'm also the chapter leader of the Kansas City chapter of Girl Development. And if you want to follow me, I'm Michelle Brush on Twitter. And you can find me if you want questions out in the hallway or walking around. So thank you very much.